Hi, my name is Rodrigo Fonseca. I'm a researcher at Microsoft Research and a professor at Brown University. And I'm very happy to be virtually here with you today, presenting our work on characterizing and optimizing serverless workloads at Microsoft. I'll be sharing our presentation today with Mohammad Shahrad, one of our co-authors. And this is joint work between Microsoft Research and Microsoft Azure, and several people listed here. I'd like to start with a brief introduction of what serverless is. So one way to view this is that serverless is a very attractive abstraction in which you pay for what you use. You have the illusion of infinite elasticity between 0 and however many instances you need. And you don't have to worry about provisioning, reserving, configuring, and patching, or managing servers. The most popular incarnation or shape that serverless comes in is called function as a service, in which you have bounded time functions that have no persistent state between invocations. You upload code, you get an endpoint to execute that code, and then you go. So for the rest of this talk, whenever I say serverless, I'm going to be talking about serverless function as a service. So what are people doing with serverless? There are many simple things that people are doing that are nonetheless very valuable, like ETL workloads, serving APIs for both mobile and web, IoT data collection and processing, and a lot of stateless processing of images and videos and translations, and check processing, and even some machine learning inference as well. There are some interesting explorations going on, trying to see what the boundary is of what you can do with serverless. So people have tried MapReduce and have tried linear algebra. There's fast video encoding, burst parallel executions like compiling functions with high parallelism, and even machine learning training. There are some limitations of serverless that people are trying to overcome, like the communication between functions, latency, lack of locality or a way to express locality, and no clear abstractions for state management. So this is all part of the future work agenda in our group and in other groups. But in this talk, we're going to focus specifically on the aspect of latency and resource usage. So let's go back to the abstraction of what serverless is. It's a very attractive abstraction. You pay for your use, you have elasticity, your life is great, right? Like if you're a developer, you can sit back and relax. If you go, however, backstage, where the cloud provider is sitting and looking at those nice seats, then you have a big challenge to provide this abstraction. Because you do have to worry about servers, they do exist, and you do have to provision them and scale and allocate and secure and isolate their workloads. You have to provide this illusion of infinite scalability. But if you want to make any money, you have to optimize for resource usage. And there's fees competition there as well. Now, there's also a big opportunity, right? Like because you have all these small units and you can finally pack them if you're smart. And there's a lot of space for innovation and offering new services, capturing new applications and new markets. One important challenge that I want to focus on is on the issue of cold starts. All serverless platforms have in common that before you are able to run a function, you have to provision a container or something similar to a container where the function will run. You have to load everything necessary to be able to get the runtime for that function ready to go. Then you finally have to load the code of the function, any data that the function needs, and only then are you ready to run. To amortize this cost of cold starts, what platforms usually do is that they'll keep the function alive, loaded in memory, ready to go for subsequent invocations. This is important because the typical cost of a cold start ranges from somewhere between 0.2 seconds to a few seconds. Of course, there's a trade-off to be played on here, right? If you decide to have no cold starts or just the first cold start for every function, you have to keep them in memory indefinitely. And this will undoubtedly waste a lot of resources. You can also opt to not waste any resources and only use what exactly you're giving customers, except that then every invocation is going to have to pay a cold start, and people are going to be very unhappy. So in this work, we want to explore and understand this trade-off space between these two extremes, such that we can eventually try to find a strategy that leads us closer to the origin of this graph. So to do that, let's first step back and examine the workload and try to understand how functions are accessed, what resources they use, and how long they take to run. So we took 2 weeks of invocations to Azure Functions in July 2019 and did an extensive characterization. So I'll refer you to the paper for more details. Here we're just going to give a glimpse of some of the findings that we have. But an important thing that I want to mention is that this workload, or a subset of the workload that we used for the paper, is actually available publicly at the URL below. So you can actually download and do your own analysis. So we first look at how frequently applications are invoked. One important thing to note here is that in Azure, functions are grouped into applications, and applications as this set of functions is the unit of resource allocation. We went back and looked at the number of daily invocations on average per each application, and this graph shows the CDF. So note that there are 8 or more orders of magnitudes difference in the number of daily invocations per app. So one thing that we can do is that we can look at the CDF and replace the x-axis with the average interval between invocations, which you can see on the top axis of this graph. So we can see that 45% of the apps in the green region are invoked on average less than once per hour over the course of many days. Furthermore, 82% of the apps in the yellow region, including the green region, are invoked on average less than once per minute. The remainder 18% of the applications in the orange region, which is the entire graph, are accessed more than once per minute on average. If we flip this graph and actually add up the invocations, starting from the most popular applications down to the least popular applications, we can see an interesting picture. That same group that occupied most of the area in the previous graph, 82% of the applications that have invocations of at most once per minute on average, corresponds to only 0.4% of the invocations. And the 18% of the applications that are invoked more frequently on average than once per minute correspond to 99.6% of the invocations. So the workload is very skewed. Another interesting point is that the average is not enough to characterize the workload. We found that invocation patterns are highly variable among different applications. There are many periodic functions, but also some very bursty functions, and very few of the applications are actually well-behaved Poisson process arrivals that are usually assumed in many simulations. The high-level point here is that there's no single one-size-fits-all solution to manage the residence times of applications that would work well. So we also looked at how this translates to memory usage. This graph shows the cumulative fraction of total memory allocated and total physical memory by all apps, sorting the apps by the number of invocations. So from least popular apps on the left to more popular apps on the right. One thing to note is that more popular apps tend to use more memory because there are more workers serving them, and this graph takes that into account as well. If we wanted to keep all the applications warm, as the other extreme plot, what would happen? So this blue region here says that those 82% least popular apps, the ones that correspond to only 0.4% of the invocations, would take 40% of all of our physical memory and 60% of the virtual memory of our revisioning just to reduce the cold starts in all of them. And another point, 90% of the applications, corresponding to about 1% of the invocations, would consume more than 50% of our physical memory. So clearly, not worth keeping everything into place. Last thing I want to talk about is the duration of function executions. This graph here shows a CDF of the minimum, average, and maximum invocation times across all applications. Note that these times do not include the cold start times. And I encourage you to look at the paper for details of how this graph was built. So about 50% of the apps on average run for less than a second. And about 75% of the apps have their maximum execution time smaller than 10 seconds. One important thing to note here is that if we look at the range of times that cold starts take, it's overlapping with a lot of the execution time of the functions. And so because these things are in the same timescales, it's very important to not ignore cold start times because they're very significant. So to summarize, our main takeaways from our observations of the workload is that the accesses are highly concentrated, like 82% of the apps are accessed less than once per minute on average and correspond to 0.4% of the accesses. But also they take about 40% of the memory if we wanted to keep them all resident. The arrival processes are highly variable and the execution times are short and very comparable to the cold start times. So if we go back to our trade-off space between the number of cold starts and the wasted memory, we saw that we can't keep functions in memory indefinitely because those will spend a lot of memory to cover very few accesses. And also that we can't ignore cold starts because the times are in the same order of magnitude as most invocations. So I'll now turn this over to Mohammad, who will talk about how we navigate this trade-off space, and ultimately how we manage to find a strategy that both reduces the number of cold starts and the memory usage of the service as a whole.
Thank you, Rodrigo. I'm Mohammad, and I will be presenting the rest of this talk. It is worth asking, what is the current state of the art? What do serverless providers do? This has been something that has been reverse engineered by many out there. For instance, Amazon Lambda. There, a fixed 10-minute keep alive policy is deployed, which means if your invocations are more than 10 minutes apart, you're going to get a cold start. And if you are lucky and your invocations are less than 10 minutes apart, you're going to enjoy no cold starts. Similarly, Azure Functions deploys a fixed 20-minute keep alive policy. Now, we were curious to understand what is it that one provider decides a 10-minute policy, another uses a 20-minute policy. So we took the entire workload of Azure Functions and simulated it for a week. What would have happened if we have deployed a different fixed keep alive policy? And the result is shown in this graph. Here, the CDF of application cold starts is shown. Ideally, we want to be to the top left of this graph where 100% of applications get 0 cold start. Even if you use the best policy, which is a no unloading policy, you're going to get still 1 cold start for the very first invocation of that application. And that is denoted with that dashed blue line. And you can see that different fixed keep alive policies can move us towards that direction, but the gains become more and more marginal. To be fair, we should look at it together with the amount of memory that is wasted for these different policies. And to do that, we basically take the third quartile of application core results, and that way we can map it towards to the right figure on the x-axis. And to the y-axis of the right figure, you can see the normalized wasted memory time to that of a 10-minute fixed keep alive policy. And as seen, if we go for longer keep alives, we can improve the application cold start, specifically third quartile core stall, but that comes with the cost of increasing the memory that is being wasted now, just sitting there without being used for function execution. The fixed keep alive policy, it doesn't work for even the most simplistic sorts of invocation patterns. If you're unlucky and your invocation is periodic, very simple and very predictable, but if it is 11 minutes apart and your provider uses a 10-minute policy, you're going to constantly get cold starts. Even if you are lucky and this fixed keep alive window can capture your invocation pattern, it is still very wasteful because it keeps function images in memory for that entire window. And in this case, for instance, if we know that invocations are 8 minutes apart, we can keep things in sleep and then pre-warm them right before they're supposed to come. So with all of these insights that we have gained and we have limitations that we have seen in the fixed policy, we have introduced the hybrid histogram policy that tries to adapt to each application as much as possible. We do pre-warming in addition to keep alive, and that allows us to eliminate cold starts while effectively reducing the memory being wasted. And we ensure that the implementation is very lightweight and allows us to track these different behaviors per application. So in order to explain that, let's go through an example together. Let's imagine that we get the first invocation. It is a cold invocation. 8 minutes later, 8 minutes after the first one finishes execution, we receive the second invocation. And we call that idle time. Idle time is the difference between execution and the next invocation arrival. And we see this 8-minute idle time, and we just take a note of that in a histogram. And if we see another observation of 8 minutes, we take another note in that histogram. And maybe after a while, we start seeing a nice pattern that for this application, idle time is mostly around 8 minutes. So you can define this window that tells us that you need to keep things in memory alive for slightly more than 3 minutes. And after an execution ends, you can keep things in a sleep and pre-warm it perhaps 6.5 minutes in. And that way we can adapt to this periodic pattern. In practice, we saw that it is very useful to define a certain cutoff boundaries. For instance, in this case, a head cutoff of 5th percentile and tail cutoff of 99th percentile, which allows eliminating outliers and ensures that these histograms run efficiently. But what matters mostly is that here, the histogram, the resolution here is minutes. And that means that if you want to go for capturing a moving history of 4 hours, you need to only keep track of 240 bins, which is very lightweight in implementation. One can imagine that if your application is infrequent, what happens is that you're going to have idle times that falls out of this histogram, and we call them out of bounds. And now, if there's only a few out of bounds, perhaps you can still be fine with that. But if we start seeing that the number of out of bounds is starting to grow, we take another approach. In that case, because invocations are infrequent, we have enough time to run complex predictors. And in this case, we use the methods that are known in time series forecast. So here, I'm going to tell you about the decision tree that we go through. When a new invocation arrives, we update the application's idle time distribution. If we see that there are too many out of bounds, we use time series forecast. Specifically, ARIMA was something that worked nicely for our workloads. If there are not too many out of bounds, we check and see if whether the histogram has captured a significant pattern. And to do that, we look at the coefficient of variation. If the histogram hasn't captured a significant pattern, we try to be conservative and adjust the histogram to its maximum size. But if we have captured a nice pattern, then we use all of these notion of pre-warming and keep aliving and adapting to different applications. And going back to where we started, here you can see the Pareto frontier for different fixed policies. And using this hybrid histogram policy, we get a more optimal Pareto frontier where application cold start is improved and there is less memory wastage. So specifically, if we have a hybrid policy that has a 4-hour histogram at its core, you can see that that's giving you the same third quartile application cold start performance to that of a 2-hour fixed policy, but with 50% less memory wastage. So we were happy about these results, and we implemented our prototype in Apache OpenWhisk. Apache OpenWhisk is an open source industry-grade serverless platform. It is used in IBM Cloud Functions. And here functions run in Docker containers. By default, it uses a 10-minute fixed keep alive policy. So it had the reference point that we wanted. And what we did was that we implemented our policy inside the load balancer within the controller. We have modified the APIs to pass those keep alive and pre-warming parameters to invokers. And the invokers that manage containers on each server, they are now aware and handle those containers according with these parameters, meaning that they can pre-warm containers at the right time, or they can terminate or pause containers at the right time. So here, I want to just show you some of the results. To the left, you can see how the application cold starts improved by going from a fixed 10-minute policy to a hybrid policy in simulations. And to the right, you see the experimental results from our Apache OpenWhisk implementation. And you can see that they're very similar. And because of the scale of the experiment was smaller, you can see that there are a lot more steps to the right figure. We saw a similar container memory reduction of around 15% in our experiments. That was the same as the simulation results were telling us. And because of this secondary factor that OpenWhisk includes language runtime in the execution time, if you prevent a cold start, you also improve the average execution time and the tail of execution times. So the good thing was that all of this happened in less than 1 millisecond of added latency. So on the critical path, we add around 800 microseconds of latency, and that was very good given all the benefits that we're getting. So to summarize, this study has provided the first characterization of an entire provider serverless workload. We have introduced a dynamic policy that allows us to manage serverless workloads more efficiently. This means reducing the cold starts that users experience, and also at the same time reducing the amount of memory that the provider consumes for these serverless workloads. Now, the good thing is that the first elements of this new policy is now running in production, and hopefully it can roll out in production fully soon. And great news for the research community is that the Azure Functions traces are now available to download. And this would hopefully allow other researchers to reproduce our results and further go and conduct other research in the serverless domain and move the frontiers of this research area. Thank you for your attention, and please look at our paper for further details.